Hey, this is Mr. Ward. I'm going to talk about section 4.2, the case of the missing diagram. And the key element of the missing diagram is you're going to be given proof situations where you're not given a drawing, and you're going to have to draw the drawing. Please make it general. Do not add any extra stuff because then is included, and these will remind you a bit of locus problems. So here's our first example. It states here, many geometry problems are stated without a diagram. Also, at times, you may be unsure of precisely what is given and what should be proved. So, example 1, if two altitudes of a triangle are congruent, then the triangle is isosceles. Now, what I want to note is that we've been told we're drawing a triangle that has, and we're drawing two altitudes in the triangle. And we're also told that those altitudes are congruent. So these are givens for us. The thing we're trying to prove is that the triangle is isosceles. So in this example stated in the if-then form, in such a sentence is a conditional statement, and the given conditions are mainly in the if clause. You can see that they're altitudes, and those altitudes are congruent. And the conclusion, whatever we're trying to prove, is in the then clause. Then the triangle is isosceles. So let's take a look. We're going to have to draw it. This really important stuff up here. Just represent the given information, but otherwise it should be as general as possible. So do not, in the setup below, do not treat the altitudes as bisecting the sides. They're not automatically medians. Maybe they are, maybe they're not. Bisection was not given. So if we do that, we're over-determining the problem. So here we have our triangle. We will call it ACD. And we've drawn these two things that are going to be altitudes. So BD and CE are the altitudes. And BD and CE are congruent because that was one of the conditional statements. So we can prove that this is isosceles with this information. So we know that this is congruent. So we know that BD is congruent to CE. And we know that this is a right angle, and that's a right angle. In fact, we also know that's a right angle. Let me make that more right, like that. So we know that stuff. We could also make them note that CD is congruent to itself by reflexive. And now we have a hypotenuse leg situation because these are right triangles. And we can prove that BCD and EDC are congruent by hypotenuse leg postulate. With that, we can also prove that angle BCD and angle EDC are congruent by theorem, by Kappa-Kadika. And I'm getting a little ahead of myself when I say theorem. And because we can prove these angles are congruent, then we can prove that the opposite sides of them are congruent by theorem 20. So this side here and this side here is congruent, and then by definition, it's isosceles. Okay. So here we've got the medians of a triangle are congruent if the triangle is equilateral. So the given is the if the triangle is equilateral, and the conclusion is the medians are congruent. So we have to start off by drawing an equilateral triangle. And the book has drawn one for you. Here's an equilateral triangle. And these are going to be the medians. Okay. So what we're trying to prove is that the medians are congruent if it's an equilateral triangle. So given it's equilateral, that means, and then given that, oops, I didn't mean to do that. Let me back up for a second here. I ended up out of the chapter, not what I wanted. And we'll blow that up again. Okay, I'm back in the chapter where I wanted to be. So we drew an equilateral triangle PZ, and RY and QX are all considered medians. And since they are medians, we have some information already. We know. So by defining them as medians, first of all, by defining it as an equilateral triangle, we know that this side, and this side are congruent. We're trying to prove that PZ, PRY, and QX are congruent. So to do that, it would be useful to be able to prove some sets of triangles are congruent. So if these three sides are congruent and these are medians, then we can also prove that YQ and ZQ are congruent. And that's splitting the same thing here and here. So that's congruent to that. That's also congruent to that. And those little bits are all congruent to each other. So now we can also make note that, let's use purple. So we can say XQ is congruent to itself. And so we can say XQY is congruent to XQZ. Then we will know that this angle here is congruent to this angle. We'll also know this angle is congruent to this angle, which you probably already knew from equilateral triangles. And we can play around with it, and eventually we will get to that this side is congruent to this median is congruent to this median is congruent to this median. Now, I'm not going to go through the whole proof right now. I'm going to let you think about it. But you might also note that since it's an equilateral triangle, all of these larger sides are congruent, and therefore we'll be able to prove a side, angle, side, and it'll be side, angle, side just rotated all the way around, and you'll be able to prove that those medians are congruent. Okay, example 3, we have the altitude to the base of an isosceles triangle bisects the vertex angle. Now, it's leaving out the words if and then, but this is a conditional statement. So we've established that it is an altitude to the base of the isosceles triangle, and that's the condition. And the then is if you have an altitude to a base of a isosceles triangle, then it bisects the vertex angle. That's really what's happening here. So we'd want to draw it. And the book draws it, but I'm going to go ahead and draw it too. So here we're going to have an isosceles triangle, and I am intentionally drawing those two sides the same color, and I'll pick a different color for the base. Okay, like that. And it's an altitude, so I'll pick this color. Since it's an altitude, it makes a right angle here and a right angle here. And we want to prove that it bisects this vertex angle, so it'd be useful to prove that this triangle is congruent to this one. By now, it should be fairly straightforward to prove these two triangles are congruent because they are right triangles. The altitude is congruent to itself. We've established this as an isosceles triangle, so the hypotenuses here are congruent, and so we can easily prove by hypotenuse leg that this left triangle is congruent to this right triangle, and by kappa kata ka, the vertex angle here is bisected because these two are congruent, and so bisection divides an angle into two congruent parts. So throughout here, you're going to need to take, and here we have the drawing. You had to take the triangles and take the description and draw what you've got. If two angles of one triangle are congruent to two angles of a second triangle, then the remaining pair of angles are congruent. By the way, this is going to prove something called the no-choice theorem. So can we do that? So we draw our two triangles. We know these two are congruent sets. Can we prove that the third set part is congruent? Well, A plus B plus C has to equal 180. A plus B is going to be something that's supplemental to C. And D plus E is going to add up to the same things. We're adding congruent angles. So we'll have two sums of congruent angles that are congruent that you would subtract from 180 to get the remaining angles. So by no choice, this remaining angle will have to be congruent. So you can prove that. But here you would just simply draw two triangles, and you would declare a couple of pairs of angles congruent, and then you would be able to establish the third one was. And that is the no-choice theorem, which you'll learn about a little bit later. So you're going to have to draw your own diagram, write the given and the conclusion, and in the terms of your diagram. So do not write the proof. So 5 through 7, so from 1 to 4, don't write the proof. That's important for this. 5 through 7 do supply a proof. So you're asked to do 2, 5, 7, and 9, I believe, for this section. So let's remind ourselves, yes, 2, 3, 5, 7, 9. So for 2 and 3, you don't need to do a proof. You just need to establish, just a reminder what you're trying to establish. You just need to write what is the given and what is the conclusion. So number 1 is one you haven't been given, but I'll work it through. So this is stated the given. So I'll actually pick number 4 because that one kind of hands it to you, and I'd rather take a look at one that is not so handed to you. So you've been given given the given and the conclusion in 2 and 3. So number 4, the bisector of the vertex angle of an isosceles triangle is perpendicular to the base. So what's the given and what's the conclusion? What's the if, the condition, and what's the then, the thing you need to prove? So what's been given is that it's a bisector of a vertex angle of an isosceles triangle. So you would need to draw your isosceles triangle. So I'm going to draw my isosceles triangle. Those two sides are the same. And then here's our base. And it's a bisector of the vertex angle. So this is the bisector. And it bisects that vertex angle into these parts. So what I'm trying to establish is that the thing that I'm trying to prove with this given information is that this bisector is perpendicular to the base. So I'm trying to prove that these are right angles. To do that, it would be helpful to prove that this and this are congruent. And we can easily do that because we can prove that this triangle is congruent to this triangle. We don't have to prove it right now, but just so you know, this side is congruent to itself. This side is congruent to this side. And this angle are congruent because the angle has been bisected. So side, angle, side proves these two triangles are congruent. These two adjacent angles are congruent to each other, and the only way two adjacent angles can be congruent is if they're right angles. Because the adjacent angles are going to be supplementary to each other, and two angles that are both supplementary and congruent can only be 90 degrees. But that's number 4. You'll have to work out number 2 and 3, but they shouldn't be terribly hard because it actually states the given and the conclusion. Now, number 5 and 7, and I believe it was 9. Now in this, I'm getting into a discussion of the problems as well. So I'll just, at this point, if you are ready to go, you can go, but you can also take note of where we are in this video, and I'm going to keep going. You can go and just do the work. Number 5, we are supposed to draw this. So we've got the altitude to a side of a scalene triangle forms two congruent angles with that side of the triangle. So the altitude to a side of a scalene triangle forms two congruent angles with that side of the triangle. So you just have to draw that scalene triangle. Okay, so it's got a side that's not congruent to another side. Okay, so there's a side. I'll make it longer. And then we'll have a third side. This one will be green, indicating they're all different. And then we'll draw an altitude. Okay, doesn't matter which one of these it is, but there's an altitude. And since it's an altitude, that's a right angle, and that's a right angle. And so the altitude of the side of the scalene triangle forms two congruent angles with that side of the triangle. Now, I have drawn everything that is a given. It's scaling. All the sides are different. This is from any vertex. I could have drawn it from any vertex. And this is an altitude, which means that it is, of course, making a right angle. It is perpendicular to the base. So from there, what you have to prove is that these two triangles are congruent, and that's not terribly hard to do. If the base of the isosceles triangle is extended in both directions, then the exterior angles formed are congruent. So that sounds weird, but if we draw it, it's not that hard. So we'll have an isosceles triangle. Okay, and we'll draw a base, and then we'll extend it in both directions like that. Okay, because it's isosceles, so we've been given it's an isosceles triangle. And we've been given that we're extending it in both directions, base in both directions. Because it's isosceles, we know that this angle is congruent to this angle. And now you should be able to see that we can easily prove that these angles are congruent using supplementary angles. Now let's just take a look at number 9. So number 9, we got line segments. The line segments joining the vertex angles of an isosceles triangle to the trisection points of its base are congruent. So that's a little trickier to think about. So let's think about the pieces of it. So it's an isosceles triangle. So let's start off by drawing the isosceles triangle. So there's an isosceles triangle. We'll draw our base. Okay, so I've drawn those yellow to indicate they're the same. Now we're going to split our base into 3 parts. So there's going to be a point here. So we're trisecting it. I'm going to use different colors, but we will be able to prove that those two are congruent. I'm going to mark this up. It's a trisection of the base, so that actually is given to us right there. So it's isosceles, and now what you need to prove, here's what you got to prove. You got to prove that this side and this segment and this segment are congruent. And you can do that because it's isosceles. These angles here are going to be congruent. Okay, so because it's isosceles, you'll be able to prove that, because side angle side will prove that this is congruent to this. And then you'll be good, because side angle side will prove these triangles, and that'll prove that this is congruent to this by kappa kappa. Okay, so the given was that we have an isosceles triangle with line segments to trisection points in the base. And then the thing you have to prove is that those line segments are congruent. And I think that's fairly straightforward to do. Now let's take a look at set C. So in set C, you're going to have to pick one of these questions, 13 through 15, set it up and complete a proof. You have to draw it. So if each pair of the opposite sides of a 4-sided figure are congruent, that makes it a rhombus. Then the segments joining opposite vertices bisect each other. So basically you're already going to have some, that some sides are congruent. So it's been given that you have a 4-sided figure with congruent sides. That could be a square, it could be a rhombus. Okay. Then the segments, and you're also being given that there are segments joining opposite vertices. What you have to prove is that those bisect each other. To prove that they bisect each other, you're going to have to prove a bunch of congruent triangles. And side will probably be your friend, and angle side angle will also be your friend for that. If a point on the base of an isosceles triangle is equidistant from the midpoints of the legs, then that point is the midpoint of the base. So this is clearly the thing you have to prove. The thing you're proving is that that point is the midpoint of the base. And the given is a point on the base of an isosceles triangle, so it's an isosceles triangle, and it's got this point on the base that's equidistant from the midpoints of the legs. So now we actually are establishing midpoints of the legs, that it's the same distance from the midpoints of those legs, and that point is also the midpoint. So you would be drawing your isosceles triangle. So there's your isosceles triangle. Here's your base. You've got some point on the base. That's the most amazing triangle base you've ever seen, isn't it? And then we also know that we're bisecting. So it's the midpoints of the legs. So these are the legs. So once we've established those are the midpoints of the legs, then we've also established that this and this are congruent to this and this. Okay, when we drew, so you'll probably need an auxiliary line in here. So if we do that and draw that, then we start to have stuff that we would need. We know that, oh, hang on, there's another thing. It's equidistant, so these red line segments are congruent. We know that this angle is congruent to this angle. Okay, and we know this side and this side and this angle are congruent. So you'll have to do some more work. Perhaps you'll have to draw some auxiliary lines on this thing, but you'll have enough information to establish this proof. The last one, but this is what is happening in that drawing. So you got to draw it. So the point of the interior of an angle between the sides is equidistant from the sides of that angle. Then the ray joining the vertex to the sides of the angle from that point bisects. Notice that from a point to a line is always taken as a length from the perpendicular of the perpendicular segment to the point of the line. So we'll draw an angle, right? There's an angle. Okay, and there's some point here. Okay, here's a point here. And we're going to have to draw a couple of line segments to the sides of the angle. And this is going to be a right angle because these distances have to be perpendicular. This is congruent to this. And you'll probably want to eventually draw an auxiliary line. We're trying to, once you do that, you will be able to establish that these two angles are congruent because you have enough information right now to do that. All right, I hope that has helped, and I'm going to stop recording.